Have you ever been at the absolute peak of a towering roller coaster, right on the edge of that massive, terrifying drop, and just wondered, wait, what actually powers this thing? I mean, there's literally no engine on those cars. Well, welcome to today's Grade 8 Physical Science Explainer on kinetic and potential energy. We're going to uncover the invisible physics that makes the whole ride possible. So, what does power a roller coaster when there's no engine roaring up front? Well, the secret is all about invisible mechanical energy. It's this amazing physical system where energy is just constantly transforming back and forth. It drives the cars along the track using nothing but the sheer power of physical laws. Section 1. Energy of position and motion. Let's take a look at the mechanical energy driving our roller coaster journey today. First up, we've got gravitational potential energy. Basically, this is the stored energy an object has just because of its position above Earth's surface. The formula for this is PE equals m times g times h. The crucial takeaway here is that this is the energy of height and position. Think about that incredibly slow creeping, click-clack climb to the very top of a coaster hill. The higher you go, the more energy you're storing up in reserve. Why? Simply because gravity is waiting to pull you down from that exact height. But what happens when you finally go over that edge? That brings us to kinetic energy. This is the energy of motion possessed by literally any moving object. The formula here is Ke equals 1/2 mv squared. As that roller coaster zooms down the massive hill, sometimes hitting speeds well over 100 miles per hour, all that stored potential energy doesn't just vanish. No, it transforms. It completely takes over as rushing, thrilling kinetic energy. When we compare these two directly, we're really just looking at two halves of the exact same mechanical energy coin. On one side, kinetic energy is all about active motion. It's the energy of right now, of actively moving. And on the flip side, gravitational potential energy is just waiting in reserve. It's stored position. It's like a giant seesaw. They constantly trade places as an object moves vertically and horizontally. Okay, section 2, mass, speed, and height. Let's dive right into the actual variables that make this energy work. We've got 4 key variables to track here. First up is m for mass, and we measure that in kilograms. Basically, heavier objects have more of both potential and kinetic energy. Next is h for height in meters, and this is what drives your potential energy. Then we have v for velocity or speed in meters per second. That one drives your kinetic energy. And lastly, g for gravity, which is a constant 9.8 meters per second squared here on Earth. Altering any single one of these physical variables is going to dramatically change the energy equations. And this brilliantly illustrates what happens at the very top of our roller coaster hill. Our gravitational potential energy is totally full. I mean, it is at its absolute peak. Meanwhile, right before the big drop, the kinetic energy is incredibly low because, well, the coaster is barely moving. All of that energy is just stored up in its high position. But check out what happens at the bottom of the drop. As the car plummets down, its height decreases, so that potential energy drops drastically. But wait, as the height goes down, the speed goes way up. It's converting all that stored potential energy directly into a surging rush of kinetic energy. The crazy part, the total mechanical energy actually stays exactly the same. It just changed its form. Moving on to section 3, solving an energy problem. It's time to put these abstract variables into action with some real numbers. Let's do the math. Let's walk through this together and find the kinetic energy of a moving ice skater. Step 1, we identify our variables. We've got a skater with a mass of 50 kilograms, and they're gliding across the ice at a velocity of 12 meters per second. Step 2, we choose our equation. Since the skater is moving, we definitely want kinetic energy. So Ke equals 1/2 mv squared. Step 3, we just solve it. We take 1/2 times the 50 kilogram mass, which gives us 25. Then we multiply that by our velocity of 12, squared, which is 144. So, 25 times 144? That gives us exactly 3,600 joules. Now to put that into perspective, 3,600 joules is roughly the energy it would take to lift a small car a few inches off the ground. Notice the unit we're using there. Energy is measured in joules, represented by a capital J. And there's a fascinating connection from our source material here. Energy and work actually share this exact same metric unit. Whenever you do work on an object, you're changing its energy, and it's all measured in joules. Section 4. Pause and check understanding. Let's test your knowledge with a really quick interactive segment to make sure this is all sticking. All right, here is your first pause check. If an apple falls from a tree, what happens to its potential energy? Go ahead and pause this explainer right now. think deeply about what's happening to the apple's stored energy as it plummets toward the ground. Okay, got it? Get ready for the answer. It decreases. Here's the immediate reasoning behind that. Losing height literally means losing gravitational potential energy. Because the apple is getting closer and closer to the ground, our h variable gets smaller. But remember, that energy isn't just lost forever. It converts directly into kinetic energy as the apple speeds up during its fall. Okay, let's try one more. Pause check 2. Which has more kinetic energy, a 10-kilogram rock moving at 2 meters per second or a 10-kilogram rock at rest? Pause again, compare the moving object to the stationary one with the exact same mass, and lock in your answer. The answer is the moving rock, for sure. Remember, kinetic energy is explicitly the energy of motion. If an object is just sitting there at rest, its velocity is 0. And if you plug a 0 into our kinetic energy equation, well, you get exactly 0 joules. So the moving rock undeniably has more energy of motion. Section 5, Recap and Transfer Question. Let's bring all these concepts together before I leave you with a final thought-provoking scenario. So to quickly summarize, total mechanical energy in a closed system is just the sum of potential and kinetic energy. Gravitational potential energy depends entirely on an object's height, its mass, and the constant pull of gravity. Kinetic energy, on the other hand, relies on how fast that mass is actually moving. Both rely heavily on mass, both are measured in joules, and as we saw with our roller coaster, energy flawlessly transforms back and forth between stored position and active motion. Which brings us to this final transfer question, directly inspired by our text. Imagine a massive 10,000-kilogram truck descending a steep hill at a perfectly constant speed. Now, its height is dropping, which means its potential energy has to be decreasing, right? But because its speed is constant, its kinetic energy isn't increasing to compensate. Instead, the driver notices the truck's brakes are starting to overheat. So, applying the conservation of energy to this real-world scenario, where did all that gravitational potential energy actually go? I want you to really think about how mechanical energy transforms into heat and friction. Thank you so much for joining me on this explainer, and keep observing the physics happening all around you.